Hi, I'm Manali Tangrikar, and this is my submission for the Robot Perception Final Exam. The problem statement of this exam is to track a given athlete in the video provided, essentially a single object tracking problem. There are a lot of challenges in tracking object tracking of video sequences. The very fact that different video sequences have different targets with different appearances, and that an object can be a target in one sequence but background in another, makes tracking a much harder problem. Uh, Plus, upon that, there are challenges due to occlusion, a rapid movement of the target object, changes in brightness, and so on. In order to solve this problem, I have used the MDNet, the multi-domain network, to track the selected object. I've also used the YOLO V3 to do the initial object detection to get the bounding boxes uh, of objects in the first frame. I have used the T4 GPU on Google Colab to run my experiments. So traditionally, a lot of convolutional neural networks are used for detection and tracking. They are very expensive to train. So one option is that we train the whole network, but during inference, we use the first few layers as feature extractor. That is, we only change the weights of the last couple of layers, uh, which are trained online. So we have the CNNs as the feature extractor, and the last few layers can be quickly trained. But the problem here is the last layers are not generic. Like uh, for the initial challenge where one object can be a target in one sequence but background in another. So in this case, that would be a problem. What MDNet does is something very clever. It rearranges the network into two parts. The first part is a shared part, and then there is a part which is independent for each domain. So the shared layers has three convolutional layers and two fully connected layers, and then there is a domain-specific layer which has k branches. And here k refers to the k number of domains, that is, each layer would be trained on one specific domain. Each of these branches contain a binary classification layer with softmax cross entropy loss that is responsible for distinguishing between the target and background in each domain. This network is trained iteratively over the k domains, and then it learns to classify between the target and the background. Moving on to the training and inference. During the training phase, a mini batch of images is created, and each image in this for each image in this mini batch, we uniformly sample a certain number of positive locations around the target and a certain number of negative locations around the target. The number the number of locations can be set according to our data set. A positive sample is is a sample which has an IOU intersection over a union of greater than 0.7 with the target object. Again, 0.7 is a threshold which is a hyperparameter and can be changed. A negative sample has an IOU of less than 0.5 with respect to the target object. These regions and then warped from the image. They're resized and then they're fed into the binary classifier to learn the domain agnostic and specific features. During the inference, just like the offline pre-training, a set of positive and negative boxes are sampled around the target which we want to track during inference. much larger number of negative boxes are sampled at this stage in order to achieve the hard negative mining. Moving on to the code. So I have reused certain parts from the homework 3 to get the bounding boxes of the object. So these are the initial codes where I download and clone and import libraries. I've also added also added the test data zip file, and I've extracted this, and then I've so the first image in the test data had a bounding box already. I've used the second image to get the bounding boxes. So I performed it. I get the detections, and so along with the class name, I have also added a counter for each object which is detected. So here we want to track the object 6. So I get the corresponding bounding boxes, and then I send this bounding box as an input to the MD net. This is just for visualizing what bounding box I was sending. And then, yeah, so we create a JSON file which has we have the frames which we have in test data are around 3,500. So we create uh, a JSON file which has paths to all these images. We also add the bounding box coordinates, the x, y, width, and height of the object which we want to track, and then uh, and and also the path where we want to save our frames after processing. All this is there in the JSON file, and then it's we create that file, and then in the next part I clone the MD net, and there are a few changes which I had to do in order to run, and then I run the tracker and send this JSON file as an argument. So here in this, we can see in the tracking, this is the file which we run, and for inference, this is a pre-trained network, and it has ImageNet and other VOT models. This is the config file from where we set which takes information from the JSON file which we've created, which takes the image list, the initial bounding box, and the paths. These are the options file has all the hyperparameters set. So we can see that for the initial training, the threshold was 0.7 for positive samples and 0.5 for the negative samples. And for the online training, that is inference, we have 0.7 and 0.3. And then after running, so it ran for all the 3,500 samples and created the same number of frames with bounding boxes. And then I just clubbed all these frames to stitch into a video. We can now see the video. Okay. I've added at 2x, but yeah. It tracks fairly well. It's a long video, maybe I'll just change the speed. It tracks even in 2x, even now. Okay, I think I think that's all I wanted to show. Thank you all. Please let me know if you have any questions.